All right, today you're going to meet your 6 best friends that we are going to get to know and love through the whole rest of this semester. So everybody got a sheet, everybody got some pencils, we good to go? All right, so let's get started. So we're going to start today by learning 6 basic functions, and then for this unit, we are going to learn different things we can do with these functions and different attributes of them, and so that's how today is going to roll. So on the top of the first page, top left, we are going to get started with f of x equals x squared. This is called the squaring function. This first time around, when we go to graph things, what we're going to do is I'm going to plug in some points so that we can see the shape. But here is my goal for you as we go through this. I want you to get to know and to love these basic functions. So I need you to be able to, from memory, be able to draw these things. So at some point over this weekend, part of your homework is to practice graphing these 6 basic functions. I have some graph paper that you can print on Canvas, and you can go ahead and give it a try. The graph paper looks just like these grids that I've given you here. That's going to be my requirement on the test, is any of the stuff that we do next week, the transformations and all the good stuff, you're going to have to do from the basic functions that you already know. Okay, so that is kind of one of the key things. That's why we're going to go through the effort of getting to know these 6 basic functions. So for the squaring function, I'm just going to go over here to the left. I'm going to make a little XY table. We learned that tables are one way to represent our values for our function. And so here we go. I'm just going to prescribe these values to us. We're going to use 3 and 2 and 1 and 0, -1, -2, and -3, just for kicks. You might say, hey, Perkster, why did you pick those values? And the only reason I picked those is because those are the ones that are going to fit on my grid. Okay, you can literally plug anything you want into the x squared, but not everything is going to be useful because it might not fit on the grid that I've given you. And so here we go. This is a nice, relaxed, simple, basic function. When I plug 3 into f of x, what is my output going to be of this function? It's going to be 9. Perfect. We're off and running. If at any point I give you a value and you do not know where that came from, or you do not understand something, please wave your hand. I'm not wearing my glasses, but you all just look like blurry blobs and I can see your hands. So just let me know and I will answer anything I can, because today is super, super important. When I put 2 into the function, what's my output? Indeed, great. And when I put 1 in, 1 squared, 1 and 0. And when I put my negatives in, -1 squared is 1 and -2 squared, 4 and 9. Okay, and those are my values. Now, when you take your test, when you do your homework, you're welcome to reproduce this table, but I'm hoping that you'll derive some efficiency and just be able to reproduce this. So now I'm going to plot the points. 3 and I go up 9, so I'm going to make a dot right here. 2, 4, make a dot right here. 1, 1, 0, 0, -1, -1, and the same thing here on the left side of this, and -3 and 9. And there's my points. Over by my drink over there is where they are. And then I'm going to connect the dots. So, whee! And I get this squaring function. It's also called a parabola. We'll spend our whole entire, I think, unit 3 focusing in on parabolas and more details about them. Just real quick, because it was part of the last test and some people struggled with this a little bit, let's identify the domain and the range of this. So my domain refers to my x values. So how far left is this graph going to go? If I had a big enough grid, how far left will this go? That is indeed true, -infinity. And then the same thing for the right. If I had a big enough grid, it's going to go to +infinity. So there's my domain. All real numbers is another way to say that. And the range, what is the lowest y value? How far down does this go? 0. And then how far up does it go? Yeah, that's a little more obvious. So I'm going to put a bracket over here because it does go through the origin, and then a parenthesis on the other side. Before I go to the next of our basic functions and introduce it, does anyone have a question so far about the squaring function, the parabola? Okay, I'm sliding to the right here. The next function that we're going to deal with, this is called the absolute value function. At some point in your math lives, I'm guessing you've seen this, but just in case you haven't, these bars right here, they tell me to do something specific. So for instance, if I have the absolute value of -11, okay, whoops, which you can't see on the screen, there it is. If I have the absolute value of -11, what do those bars tell me to do with that? Anybody know? You just make it positive. Yeah, absolute value just means whatever is inside the bars, you make it positive. So the absolute value of -11 is 11. The absolute value of 9, if the number is already positive that you're taking the absolute value of, it just stays the way it is 9. And then sometimes students ask, what about 0? Because 0 is not considered positive or negative, and the absolute value of 0 is just 0. So when you see those absolute value bars, it's just saying, give me the value part of this. I don't want any sign. Everything's going to be positive. So we're going to use that fact as we make our table. So again, I'm going to make a cute little table of values right here. Again, I'm going to prescribe these values. I'm just giving a variety. So I'm going to say 5 and 2 and 0 and -1 and -6. We'll use those values right there. I'm pausing for a moment just to make sure you're keeping up with me. So from my brief little introduction to absolute value, that's right there. When I put 5 into the absolute value function, what is the output going to be, do you think? Oh, yes, you are totally right, 5. And when I put 2 in, I'm going to get, and I already told you 0 will give you 0. How about -1? When I put that in, what's the output going to be? Yep, and -6 is going to give me, excellent, you guys are doing a great job. I'm hearing a lot of voices. But if you are confused, if you are not one of those voices, please ask me a question. Let's get that out in the open so that we can all be confident in what we're doing. So plotting these points, 5, 5, and 2, 2, 0, 0, -1, 1, and then -6, 6. And what you get with the absolute value, I don't have a straight edge with me, but I'm going to do the best I can. You get what is a V. Oops, I kind of missed that dot there. Apologize for that. There we go. My absolute value function is a V. Before I move on, does anyone not see, is there any confusion about where any of those values came from for the absolute value function? Are we doing okay? I'm going to move to the bottom of the page now. On the left side, we've got our cubic function is next. Once again, I'm going to make a cute little table of values. Now, the cubic function, what we see, or what we will see, is these values, since we're cubing them, get big very fast. So I'm kind of limited with my small little grid of the values I'm going to put in. So I'm going to put 2, 1, 0, -1, -2 into this function. Again, that's not, you can plug anything you want into the cubic function. Okay, but I am just limited to those because I want things that I'm going to be able to plot. So when I put 2 in, 2 cubed is going to give me what? Yes, that is great. Thank you for your multiplication prowess. And then 1 cubed is 1 and 0 cubed is 0. How about when I cube a negative number? What's -1 cubed going to be? Yep, thank you. And then -2 cubes, -8. Excellent. Great job. Again, I'm just pausing so you can be caught up with your writing. I don't want to lose you. I'm hoping this is relatively simple. It's just a matter of committing it to memory, I think, is the big deal of what we're doing here. So I'm going to plot these points. We've got 2 and 8, so that's going to be right there, and 1 and 1, and 0, 0, and -1, -1, and -2, -8. The cubic function kind of looks like a river when you're looking at it from space. If you ever take calculus, if that's in your math future, a lot of fun stuff happens right around the origin in the cubic function. Okay, but you need to know how to take derivatives and integrate things in order to figure that out. So that's the joy of calculus. But for us, for now, we are just going to graph it. What I would like you to do, I'm going to give you 15 seconds. If you wouldn't mind writing down what the domain and the range are for the cubic function, please. So the domain of the cubic function, I know that it might not be obvious, but how far left is this going to go if I had a grid big enough? Yeah, negative infinity. It's going that way slowly, but it's going to the left. You can put any negative number into the cubic function. There's no restriction. How about to the right? How far to the right is the cubic function going to go? Yeah, same thing. Now, the range is a little more obvious from our graph. The range, how far down is this going to go? Indeed, and then positive infinity. Great. Once again, I don't want to move on. If there's any question, comment, or concern, does anyone have anything that they'd like to chat about as far as the cubic function is concerned? All right, here's 4. This is our 4th of our 6 friends. This next one's the square root function. Not really an interesting name, but we'll... Now, the square root function is the first and only of our 6 basic function that is going to have a limit on the values I can plug in. And notice our Cartesian plane doesn't talk about complex numbers. We'll get to those when we discuss the square root function in more detail. I think that's in Unit 4 or Unit 5. Pretty sure it's Unit 4. But for now, in our square root, we're not going to be able to take the square root of negative numbers. Okay, we don't have imaginary numbers. I'm pretending that they don't exist at this point. So that means the smallest value, what's the smallest value I can take the square root of then? Yes, indeed, 0. Now I'm going to be systematic in the values I pick because I want to be able to do this quickly and easily. So the values of x that I plug in are going to be values that I can quickly and cleanly take the square root of. I don't want any decimals. I don't want any irrational numbers. So I am going to put in these numbers intentionally. 1, I'm going to put in 4, I'm going to put in 9. I'm being very strategic. I would put in 16, but again, I just found 10 by 10 grids online, so that's why they cut and pasted onto this sheet. So now when I take the square root of 0, we get 0. What's the square root of 1? Yep, square root of 4. 2, square root of 9. Excellent, great job. And so here's what the square root looks like. At 0, I got 0, 0. I've got 1, 1. Then I go out to 4, and I go 2. And then I go out 9 and up 3. And so the square root function is actually like half a parabola, the top half of it. We wouldn't have the bottom half of the parabola on this side because then it wouldn't be a function. So that's why we're not really chatting about it at all. And again, if you have any questions about this, feel free. But in the meantime, if you would take 20 seconds and write down what the domain and the range of that are, that would be super fun and helpful. So the domain, where do the x values start on this function? Yep, 0, great. And then you can see they go to infinity. I don't think that's going to be in dispute. I'm going to put a bracket at the 0 end of that. How about the range? Where do the y values start on this? Again, 0, great job. And I'll put a bracket there because the origin is included. All right, we'll come back. We'll talk about some other things with regard to those functions in a few minutes. But in the meantime, I'm flipping the page. We've got 2 more basic functions to talk about. The next one is the cube root function. So once again, I'm going to make a little XY table. Okay, again, this is what you do when you get in a pinch on a test or on a homework. But again, I'm hoping that after you do this 2 or 3 or 19 times that you begin to remember what the shapes of these graphs are and can reproduce them. Once again, like the square root, the cube root, I am just going to put inputs in that I can take the cube root of easily. So I'm going to use 8 and 1 and 0 and -1 and -8. Those are going to be my x values that I'm going to plug in, and I'm going to see what the cube root will be. So if you need your calculator, go for it. Or if you know what times itself 3 times gives you 8, and the answer is 2. And what times itself 3 times gives you 1. Whoops. What times itself 3 times gives you 0? That's 0. You don't have to worry about it. Thank you for looking, though. What times itself 3 times gives you -1, and then finally -8. And there's my cube root values. So my cube root, when I go to plot these, I go over 8, and then I go up 2. There's my first point, and 1, 1, and 0, 0, and -1, -1, and -8, -2. The cube root looks suspiciously similar to the cubed graph, except this one is going more left-right than up-down, like the x cubed graph. There is a reason for that relationship. That'll be something we talk about in Unit 5. When we talk about there's a relationship between a couple of these different functions. But for now, that you just need to know how to graph it. Last but not least, this is probably the function you're most familiar with, because if you took intermediate algebra, we took like a unit and a half to talk about this. This one right here is an identity function. And it's the basis of our linear functions. If you remember y equals mx plus b, maybe you have nightmares about it because you didn't enjoy that unit in intermediate algebra. It's called the identity function because, as you can see, whatever x value you put in is just the x value, or excuse me, is just the y value that you get out. So whatever x's you pick, that's also going to be the y. So for instance, if I pick the x value 7 and 2 and 0 and -4 and -5, where did I get those from? I'm just picking whatever I want. I'm the one with the pen, so I picked you. If you're doing this, you can pick any x values you like. And whatever you plug in, notice here's what the identity function says. Whatever's in the parentheses, whatever you plug in is what you get out. Okay, you don't do anything to it. So when I plug in 7, I get 7 out. When I plug in 2, I get 2 out. And the same thing for 0 and -4 and -5. So this is the last of our 6 basic functions we're going to talk about today. There will be other basic functions we talk about as we go through this class. And the next, in Unit 4, I think we talk about 1 over x and 1 over x squared. And but you don't have to worry about any of those right now. And so when I plot these points, I've got 7 and 7 and 2 and 2 and 0, 0 and -4, -4 and -5, -5. This should be a line. I don't have a straight edge. Again, I didn't bring one with me. Professor Perkins is not prepared. You can leave that in your reviews. There we go. There's my line. All right, well, congratulations. You just made 6 new friends. We're going to do a lot of things with those over the semester. Questions so far? All right, well, what we're going to do with the rest of our section is we're going to talk about some attributes of these graphs and other graphs that we're going to take advantage of. So the next one is the idea of what does it mean for a function to be continuous? We are going to define the idea of continuity. So the definition of continuous is this. I'm not going to give you the mathematical definition. You're not there yet. You need a little calculus. You need to understand the minute changes. So I'm just going to give you kind of a description of what it means to be continuous, and that'll do for us. And so a function is continuous over an interval if, and here's the very technical definition, if you can trace it without lifting your pencil. finger or pen or crayon or whatever you happen to be writing with. So a function is continuous over an interval if you can trace it without lifting your pencil. So some functions are going to be continuous everywhere, and we're going to go back and look at some of our basic functions. But some functions, like you can see below in the examples that first couple examples I have for us, some things are continuous, not everywhere, but at certain intervals. And so what we do is we use intervals to describe where things are continuous. So for instance, example 1. Example 1 I'm going to do, and the question that you're going to be asked on homework, the question you're going to be asked on the test is, on what open intervals is this continuous? Now, in future problems, I'm just going to write continuous, because that's a lot of words. I'm feeling pretty lazy today. Now, I'm going to say the same thing to you today that I said to you when we were talking about reading graphs last time. We are going to give the intervals along the x-axis where the y-intervals that the graph produces are continuous. Okay, so our intervals are the x-intervals. If you need to make note of that, on the side, write a note for yourself. We give the x-intervals that produce the continuous y values. For a few of you, and this was fully expected by me, so there's nothing wrong with you. You'll overcome this. But for a few of you on this last test, you gave me the y-intervals for things. Okay, so when you're reading the graphs, you got to learn you're giving the x values that produce, in this case, the continuous y values. So I can trace this lower part right here. I can trace this, I think we would all agree, without lifting my pen. Do you agree with that? So it's continuous right here, but here's the problem. I have a break. I have a break right here. I have to lift my pen to get to right there. So what we would call this right here is we call this a point of discontinuity. It's a place where the graph, it's not really a problem, but it's as far as continuity is concerned, it's a place where the graph is no longer continuous. So I have two intervals, though, where I don't have to lift my pen. I just have one point of discontinuity. Man, when that air goes off, I'm talking really loud. So the first one, I'm going to describe the x values that produce these y values that I'm tracing with my pen. So what is the lowest x value that is producing the y values here? What's the furthest left this part that I'm tracing goes? Yeah, and I'm just going to, along the axis, it goes to negative infinity. And what is the x value where this stops? What is the x value where that break happens? 2. Okay, so right here, I'm tracing along the axis right there. And so I'm going to put 2. When we are describing continuity, now this is not something I will be super fussy about, but the preference would be, okay, if you're going to go beyond this in math, you'll probably encounter an instructor that will be fussy about this. For continuity, we use open intervals. So we just use parentheses on both sides. And the reason for that is because of the mathematical definition of continuity, which I didn't share with you because you're not technically ready for it. Okay, so you're just going to have to trust the Perkster on that. So then how would we describe the x values that produce these y values up here that I'm now tracing? How would we describe those x values? Well, what's the lowest x value? 2. Okay. So usually we use a comma. We're not using a union. We're not describing a full set of values, just a comma. We're listing the different intervals. So 2. And then what's the highest x value we have here? Yeah, there's an arrow there, and so that is infinity. So that's where this is continuous. Okay, so I would like you to make an attempt. Okay, you're going to give your best attempt at this. Example 2, you're going to do the same thing. I would like you to denote for me the open intervals where this is continuous in example 2. How many intervals do we have on this one? There's going to be 3, right? There's 3 parts to this graph. There's 2 places. If I'm just going completely left to right, there's 2 places where I have to lift my pen and go to the next part. So there's 2 breaks in this graph. So the first interval to describe the leftmost part, again, I'm not describing the y values, okay? So you're not giving me y, you're giving me the x's that produce these y values. And so those x's are negative infinity, and then it stops here at -4. Anybody get something different that we need to talk about or clarify? Again, you're going to get better at reading graphs because we're going to do a whole lot of it. And I'm going to say it a bunch more times. You're probably already tired of hearing it, and that's good. You're giving the x values that produce these y values. So up top, what x values produce these y values that I'm now tracing at the top? -4 to 3, great. Again, you're giving the x's, that's excellent work. And then one final time, I've got one more interval, so I'm going to use another comma. And then what are the x values that describe this interval right here? 3 to infinity. Excellent, well done, appreciate it. I got one more example of this, then we're going to go back and look at just a couple of our basic functions. If you would flip the page, top of page 3. Before you get going, I want to tell you 2 things about this. Some graphs, if we have time when we get a little later in the class, I'll be able to tell you what produces something like this. This is a hole in the graph. It's called, the technical word for it is called a removable. I don't know how to spell removable, I'm just realizing. So I'm going to put an E. We'll put an E in there. That might be wrong. A removable discontinuity. The reason it's called that is I could define a value to fill in the hole, and then it would be completely continuous. Unlike the previous ones where the graph, you had to make some great leap over a chasm, okay, that is not something you can remove. Now, one note I want to make is there are 2 separate intervals you're going to describe for me. I had a student last semester, super clever, said, hey, Perkster, I don't have to lift my pencil. I could just go around the outside of that hole right there. And technically, that's right for the graph, but that hole is just for us. It's just a break in the graph, okay? So it's something you do have to leap over. So I would like you, please, to describe for me what are the intervals, there's 2 of them, on which this function is continuous, okay? Left of the hole and right of the hole. So the interval left of the break, the left of that removable discontinuity is negative infinity up to 5. That's the x values, and then comma, and then the interval to the right of that hole or that break is 5 to infinity, and that's the 2 intervals that you should have given me. We doing okay with continuity and what it means and what it looks like? All right, if we do me a favor, flip back to the front page. We're just going to real quick look at a couple of our basic functions. So the first one we'll look at is the parabola. So when I'm tracing the parabola, do I have to lift up my pen at all? No. So if I ask you, what is the interval on which this is continuous? Since I don't have to lift up my pen, and I don't expect that I ever would, I would say for this one that it's negative infinity to positive infinity. Okay, that the whole graph is continuous. It's continuous everywhere. And that would be the same answer you would give for the absolute value graph, for the cubic function, for the cube root function, and the identity. All of those are continuous everywhere. Okay, there's never any place where you have to pick up your pen. There is one of our graphs that does have a little bit of a limit on the continuity, and that is our square root function. So what I would like you to do real quick is propose to me what the interval of continuity. Where is this continuous? And what did you write down? Where does this graph start being continuous? 0, and then goes to infinity. There you go. Once the graph starts, you never have to pick up your pen, but there is the problem of where does the graph start? That's about all I have to say about continuity. That's my expectation for you, is that you can identify where a function is continuous by the test of, do I have to lift my pencil or my pen? And then you can describe for me the x intervals that produce the continuous y values. If you have a question about continuity, be sure to ask it. Otherwise, I'm turning back to page 3. The second attribute of functions that we are going to talk about, we're going to be interested in at different points over this semester, is the idea of if a function is increasing or decreasing in constant. So real quick, just tell me the language. I am sure if I asked you, you could identify in a graph. What does it mean for something to increase? It's getting bigger. The value is getting larger. Okay, that's what it means to increase. So as I'm looking at the function, I would see that the values are getting bigger. How about decreasing? What does it mean for something to decrease? It's smaller. Perfect. And what does it mean for something to be constant? Stays the same. Excellent. So you have told me intuitively what this means, and that is fantastic. And so what I'm going to now tell you is what the mathematical definition of increasing and decreasing and constant are. And then we're going to learn how to identify those on our graphs and to give our intervals. So a function is increasing on an interval if the following is true. If for the situation where you have x1 is less than x2, I'm going to stop there. All that means, okay, this is just the fancy math way to say that you are reading your graph from left to right. You are going from smaller x values to bigger x values, and that's how you're going to proceed down the number line. So we don't read our graphs when we're looking for increasing and decreasing and constant. We don't look at them from right to left. We always start on the left, the negative side, and we proceed through. So we know something's increasing if for a x1 that is smaller than the x2, then we know the outputs, the function value at x1 is going to be less than the function value at x2. Now you're going to write that down, and then I'm going to show you on one of our graphs, okay, what that is actually saying, what that means. So I'm going to go up to example 5. Example 5 is just this little graph that I made up and I graphed. And what we are eventually going to do is we are going to identify where is this graph increasing, where is it decreasing, and then where is it constant. Now I am almost positive that if I ask you just look at the graph, and as we go from left to right, we've got three things happening. We've got this first thing, and then something happens in the middle, and then something happens over on the right. Which part of this graph is increasing? The left, the middle, or the right? The left, right? The y values are clearly getting bigger. As I trace this graph from left to right, I'm going up, 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 up. That's increasing. We can all agree on that. Now, what I want to show you is what does that mathematical definition mean? So the mathematical definition is saying this. For an x1 that is less than an x2. So I'm just putting some space here so that they're far apart. But notice my x1 is less than my x2. Meaning I'm reading from left to right. That's what I told you that means. Then what the definition says is when I compare those function values, right here, this is the function value at x1. And then up here, this is the function value at x2. If you have an increasing graph, then the function value at x1 should be less than the function value at x2. Okay, which we have right here. And I think we could all agree now that we can see the picture that that is indeed what's happening. So once again, I'm going to reiterate, when I ask you, and I will ask you, this is going to be on the test, it's going to be on the homework, it's going to be on the quiz that you should be taking as you go through this section. When I say, where is this function increasing? You are going to give me the x values that produce these increasing y values. So this is increasing. Again, there's the arrow here. So that means this graph's going to keep going left forever. So it's increasing from negative infinity. And then it stops, there we go, stops increasing at this peak right here, which is the x value, -4. So far, so good. We doing all right? I'm going to go back down to my definitions. That's increasing. Decreasing says something super similar. The function is decreasing on an interval if for my x1 less than x2. Once again, that's saying the same thing as before. Just means I'm reading the graph from left to right. Then, and I'm noticing I left my n off the then on the previous one, so I'm going to add it in so it looks like I didn't forget it. Then in this case, if something is decreasing, then the first y value is going to be bigger than the second y value as I go left to right. And I'm going to show you that on the picture again, because I know even though it's probably very intuitive just to look at the graph, sometimes mathematical definitions seem to make things more complicated than they need to be. So I'm going to slide back down. I'm going to try to keep that in view in case you're not caught up with the writing. So example 5 that we were just looking at, we already determined that that part 1, the left part, was increasing. So which one's decreasing, the middle part or the right part? Clearly, the middle part is decreasing. As I trace it from left to right, my values are getting smaller and smaller. So once again, what does this definition mean? Well, this definition means if I pick an x1 less than an x2, so here's my x1 and my x2, that the function values associated with them uh-oh, my pen's running out of ink. Don't do this to me. There we go. So you can see that the first x is smaller than the second x, but the y value of the first x is bigger than the y value of the second x. And that is what this definition is just trying to communicate. So I'm now going to write the interval on which this is decreasing. It's decreasing from this peak up here, which we said happened at -4. And it stops decreasing right here at this elbow right here, which is at 5. So there's my interval, -4 to 5. One more, the last one, f is constant, which you told me means that it's not changing. If for x1 less than x2, again, that just means I'm reading the graph from left to right. Then this time, if it's not changing, how do you think the function values are going to relate if this is unchanging? They are going to be equal. Perfect. Yes. It's constant if the function values are just equal in this interval. So by process of elimination from my example 5, we see that the right-hand interval is the constant one. And so it starts being constant at that elbow at 5. And then there's no other intervals. There's no other changes that I'm made aware of because I got that arrow. So it goes to infinity. So there is my increasing, decreasing, and constant. So I'm just going to have you do this for a couple different examples. Yes, what's the question? How did I get what value? Which one? Okay, so remember we give the x values that produce those decreasing y values. So the graph starts decreasing, trying to find a novel color. I've made a big mess of this graph. The graph starts decreasing right here at that peak, and that is the x value -4. And then it stops decreasing right here at this elbow, and that is the x value 5. So from -4 to 5, those x values produce the decreasing y values. All right, well, you're going to give it a try. You're going to do this several times. So let's just start with the example that's right next door, example 6. So for example 6, what you're going to do is you're going to write down the intervals where this function is increasing, decreasing, and constant. And spoilers, there might be more than one interval. And for other examples, there might be no interval where it's doing one of those things. It doesn't have to. I'm going to get started. I'm just going to look at the graph. I'm going to start reading it from left to right. And so this first interval that I have is the graph increasing, decreasing, or constant on this first bit. Okay, this is constant. So again, we give the intervals on the x-axis. I notice I have an arrow. So the furthest to the left this is going to go is -infinity. And then where does it stop being constant? At what x value? -5 right here. That's where the cusp is. So -5. We so far so good. Anybody got something different? Anybody confused? Please speak up. Then what does the graph start doing? At this point, it becomes what? Increasing. So it starts increasing at this x value of -5. And where do we hit that peak? Where does it stop increasing? Okay, that's -2 right there. And now what does it do? It starts decreasing at -2. And then where do we hit the elbow? Where does it stop decreasing? Okay, great, at 1. And then last but not least, my final interval is it's constant again. So that again, I'm going to use a comma. We don't use a union. We only use union for the intervals when it's domain and range, because domain and range are all one thing. For continuous, for increasing and decreasing, these are all separate intervals. Okay, that's why we use a comma here. So then it starts doing it from 1 to infinity, and there we go. A little better? Doing okay? All right, we're going to slide up to example 4 then. Do the same thing, please. Where is this increasing, decreasing, or constant? All right, again, I'm going to just start tracing from the left part of the graph and go to the right. So when I start over here on the left, what's the graph doing to begin with? Decreasing. So it's decreasing from negative infinity, and then it stops decreasing down here at this cusp at -6. Then it turns, and I think we would all agree now it's going up, 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 up. So it's increasing from -6 to 0, right at the y-axis. And then it starts decreasing again. So comma here in the decreasing column, decreasing row, and it's decreasing from 0 to infinity. So this one's not constant at all, so I'm just going to leave that blank, or you don't even have to write it if you don't want to, but we are done. I've got one more example of increasing, decreasing, constant. Go back to the front page, please. And let's go to the absolute value graph. That seems like a decent one to go ahead and look at. And on the absolute value graph, I'd like you to identify where is that increasing, decreasing, or constant. Again, following the graph from left to right, I start over here on the left. The absolute value is doing what to begin with? We are decreasing. We're going downhill, and it's decreasing from negative infinity all the way to the cusp in the middle at 0. And then it turns around and it starts increasing. So it's increasing from 0 to infinity. Once again, it's not constant. So if you didn't write the word, that's fine. I'm just going to leave that spot blank. Okay, anybody having trouble identifying increasing, decreasing, constant, or telling me what interval it is? All right, we got one more topic for the day, dealing with our new 6 favorite functions. And so I'm on page 4. The last bit we're going to talk about with respect to our functions is what's called symmetry, or it's called being symmetric. If something is symmetric, what does that word mean? Sort of. If something is symmetric, it means it's the same on both sides. Okay, so if you're not familiar with that word, when something is symmetric, it means the same on both sides. So if you've had biology class, or if you're going to take it, your biology teacher may have told you that more or less the human body is symmetric. Okay, if you took a knife and sliced it down the middle, there's some things that are not exactly symmetric, but it's more or less the same on both sides. Okay, so that's kind of how you would use that word. So there's 2 types of symmetry. There's 2 situations of functions when they are symmetric. So the first one is where something is symmetric with respect to the y-axis. Meaning if I treat the y-axis like the inside of a greeting card, like the spine of a greeting card, if I fold along the y-axis, I'm going to have the same thing on both sides. And what we call something symmetric to the y-axis is we call that an even function. Here's what I would like you to do. I want you to go back to the 6 basic functions, and I want you to hypothesize which ones you know. Put a little e or write the word even by the ones that are symmetric with respect to the y-axis. Spoilers, there's going to be 2. All right, somebody tell me, what's one of the graphs that's symmetrical with respect to the y-axis? Okay, the squared function. Yes, this is an even function. Okay, so if you're reading along and you're told that a function is an even function, that means it's symmetric about the y-axis. So notice, if I had the ability to fold this graph along the y-axis, I have the exact same thing on both sides. What's the other one that's an even function? Absolute value, yes. Now, as I'm sure you're expecting, okay, just like with continuity, folding is kind of just our way of seeing it. There's a more mathematical definition, and I'm gonna show you what the mathematical definition is before writing it out. So something is even if this is true. If I go, I'm gonna demonstrate this on the absolute value graph. If I go the same distance, positive and negative. So for instance, if this is x, and then this is negative x. So notice I've gone the same distance in left and right. Would everybody agree with that? So you know something is even. This is the mathematical test, is if you go the same distance left and right, then you end up at the same y value. So f of x and f of negative x, I'm just going to put a giant equal sign between them. So if you go the same distance left and right, then you are at equal y values. That's what makes something even. Just in case anybody's copying the picture, I'm just leaving it there for a second, but I'm going to write the same thing over underneath the word even on page 4. So I'm going to page 4 now. So we know something is symmetric with respect to the y-axis if the function value at negative x, meaning I've gone left a certain distance, is equal to the function value at x, meaning I've gone right the same distance. That is the test, or that's the determining factor. All right, the second type of symmetry that we're going to look for in functions is called symmetry with respect to the origin. So this time we're not symmetric about a line like the y-axis. We're symmetric about the origin, which is a point. When something is symmetric with respect to the origin is called odd. We'll come back to that. I'll tell you the test, but I'm going to come over here to the front page. I'm going to show you pictorially, because this is not quite as intuitive as even. The cubic function, this is an example of an odd function. So if you want to know, hey, Perkster, how can I tell just from the picture without doing anything? Great question. Here's how you would tell. I'm going to put my pen right at the origin. And now what I'm going to do is I'm going to spin my paper 180 degrees. When I spin my paper 180 degrees, it's getting caught on something. I'm going to try to do this. When I spin the paper 180 degrees, do I get the same looking graph? Yes. So that is the picture test. You might make a note for yourself, because on the test, I'm going to give you a picture and ask you if it's even, odd, or neither. So 3 points if you remember the picture test. So the picture test is if you can spin the graph 180 degrees and you get the same picture, it's symmetric with respect to the origin. There are 2 other of the basic graphs that are odd. I'm going to give you 30 seconds. Identify or hypothesize what ones you think they are. What are they? Which graphs are odd graphs? Cube root, yeah, that sounds great to me. Good call. The cube root right here, this is an odd graph. And what else? The identity is an odd graph. So again, I want to show you with the picture what it means to be odd. I'm going to use the identity function just to show you this. So it involves the same sort of thing. If I go the same distance left and right, so I've gone x units in the positive direction, I've gone negative x units backwards. Now notice if this was even, we'd get the exact same function value. But notice with odd, here's what we get. Here's f of x, here's f of negative x. They're not equal, but they are opposite values. So if you go the same distance in the positive and the negative direction from the origin, so you go x and negative x, then the function values you get are opposites of each other. They're the same value, but they have different signs. So once again, I'm going to write this down on page 4. And then we have one more thing we're going to do, and then you're done with section 2.1. So congratulations. So here, what we will say is if we go in the negative direction, then what we do is we get the opposite. So I'm putting a negative out in front of f of x. So the last thing we're going to do, we'll either do 2 or 3 of these examples, just depending on what time allows. We are going to determine analytically if a function we're given is even or odd or neither. And so let me just show you real quick with a nice simple function. So I'm going to come over here onto the side, and I'm going to say we're going to determine if f of x equals x squared is even, odd, or neither. Now, we already saw from the picture x squared is even. We know that. Okay, we saw we could fold the graph. So I just want to show you what the analytic test is. Okay, so when you do the analytic test to determine if a function's even, odd, or neither, you're always going to start with the following thing. You're always going to start. Notice whether it's even or whether it's odd, both of these statements involve the function value at negative x. So you're always going to start with f of negative x, meaning I'm going to take my function and I'm going to plug a negative x into my function, and I'm going to see what happens. When we were evaluating function values, I told you my habit is to do the following. This is x squared, so what I'm going to do is I'm going to put a parentheses squared. And now I'm going to fill in the parentheses with what's inside the function, which is a negative x. So I'm going to put a negative x here. And now we just do a little arithmetic. What's negative times negative? What are you always going to get when you have a negative times a negative? When you square a negative value, you always get positive. So a negative x squared is going to be the same thing as a positive x squared. I know it seems like a simple thing, and it really is a simple thing, but I know it's a little bit goofy. And so then you're going to ask yourself the following question with whatever function you're testing. If it's even, this is the exact thing I started with. If it's odd, this is the exact opposite of what I started with. If it's neither, then it's neither of those things. So x squared, is that the same thing I started with, or is it the opposite of what I started with? It's the same thing that I started with, right? Would you agree with that now that you see it? I understand why you said the opposite, and that's a great hypothesis. I appreciate you playing. Okay, so that is equal to f of x. And so that's why this would be even. Now, yes, you're going to do a few of these, and you're going to see the pattern. Even and odd are named for the powers that tend to give you whether they are even or odd. But I will ask you on the test to do just this thing, whether you know intuitively it's even, odd, or neither or not. Okay, so please practice this. Please practice doing this test. So we're going to do this right here. I think we'll have time for all 3 of them. So what I would like you to do is make your best attempt. Okay, this is your first one. I know you're probably going to goof it up a little bit, and that's okay. Give your best attempt at this next example. Is f of x equals 8x to the 4th minus 3x squared even, odd, or neither? I'm going to start with this statement, f of negative x. Okay, that's always where we start. So I'm taking my original function. This is what I started with right here that I've given you. And I'm going to plug a negative x everywhere I see my variables. So I've got 8 times parentheses to the fourth minus 3 times parentheses to the second. And in both of those parentheses, I'm going to put a negative x. And so the question becomes, when I take a negative number and I raise it to itself 4 times, what happens to it? Is it negative or positive? It's going to be positive. So that becomes 8x to the fourth. And then when I take a negative number and I square it, we just saw that's going to become positive. So that stays negative 3x squared. And then the question is this the same thing I started with? Is it the opposite or is it neither? It's the same, 8x to the fourth minus 3x squared. So that's equal to f of x. It's the same thing. That's why that's even. Now, I would caution you, don't just look and say, oh, all the exponents are even. It must be an even function. Because if I made one minor change to that and kept the powers the same, it would not be even anymore. It would be neither. Okay, so be super careful. Don't just make general statements that might not be true. Next thing, determine this next one. Even, odd, or neither. Again, you might goof it up. That is okay. You're getting experience right now. This one, you might have the right sense of what's going on. I understand if you're struggling a touch with the notation. So again, we're getting experience here. So if you didn't quite get it, forgive yourself. It's totally okay. So I have f of negative x. That's always what I start with. So I've got 6 times whatever I'm plugging in cubed minus 9 times whatever I'm plugging in. And I am plugging in a negative x into both of these. So now the question is, when you cube a negative number, is the result positive or negative? Negative. So what I'm going to do is I'm going to rewrite this instead of 6 and the negative inside the parentheses. I'm going to write this as negative 6x cubed. You just told me that when I cube this negative, I'm going to have a negative value. So that might be the place you probably knew that, but you might not have known how to write that down. I get it. And then over here, I've got negative 9 times negative x. A negative times a negative is positive 9x. And so again, the question is, do I have the exact same thing? Do I have the exact opposite, or is it neither? It's the opposite. We started with a positive 6x cubed. It became a negative 6x cubed. We started with a negative 9x. It became a positive. So the signs are exactly opposite. So this is the opposite of what I started with. It's the opposite of f of x. And so that makes this odd. Again, one more just to get the experience. So the last one, even, odd, or neither. So one final time, I start off with the statement f of negative x. That's always, when I ask you if something's even, odd, or neither, and I don't give you the picture, and you're doing it analytically, that's always where you start. So I have 3 times whatever I'm plugging in squared, plus 5 times whatever I'm plugging in. So I'm going to put a negative x into both those spots. Well, we saw from a previous problem that when I square a negative, I get a positive. So that's just 3x squared. And then 5 times negative x is negative 5x. So the question is that what I started with? No. Is it the opposite of what I started with? No, because the 3x is the same. Excuse me, the 3x squared is the same, but the 5x is the opposite. So we got a little bit of everything going on. So this is an example of a neither problem. Okay, it's not even, it's not odd, it's neither.